Now, before we get into this example, I'm just going to recap a couple of rules, general rules you can follow for working out NMR problems, whether that's carbon NMR or proton NMR. On the left, we're going to put down some things I'm going to use for this problem. So number one is the number of peaks in the spectra, that is equal to the number of distinct carbon environments. So for example, if you have 3 peaks, there are 3 unique carbon environments. Number two, the greater the electronegativity of the environment. So what do I mean by that? If you have neighboring oxygens, fluorines, nitrogens attached in that carbon environment, that will lead to equals a greater chemical shift. So that symbol there is the chemical shift symbol, that one there. And then number three, this is more so for proton NMR, but it can be used loosely for carbon NMR, and that basically means the height of the peak is equal to an indication of the number of carbons in a environment. Now with proton NMR, you have the area under the peak, which is the integration, and that tells you exactly how many hydrogens are in that particular environment. But with the carbon NMR, as you can see, the peaks, they're not really peaks, they're just almost like sharp lines. But generally, if you have like one line, like double the height of the other one, that suggests there may be 2 carbons in the same environment next to a different one. And it's just sort of a loose rule you can use to help you get to the answer quickly. These are the 3 that I'm going to be using today in identifying the carbon environments in this molecule. So it says, using the numbers on the diagram of stoichiomic acid structure, indicate which carbon atoms in the molecule are responsible for each C13 NMR spectrum, the precise order of carbons within the group, and the group of 3 are not required. But what we're going to do, we're going to attempt to put them all in. So I'm going to start with the easiest one, which is utilizing rule number 2. The greater the electronegativity of the environment, the greater the chemical shift. And the one that jumps out to me immediately is this one. You have a carbon, which is that dot there, directly attached to an oxygen, a C double bond O, and an OH to the other side. And that is going to have the greatest chemical shift. That has to be that carboxylic acid carbon, and this is confirmed by the data table, up between 200 is going to be that one there. So that's number 1. Okay, the next one is the double bonded carbons. So double bonded carbons, according to the data sheet that we're using today, they're about between 120 to 140. Number 2 is closer to the C double bond OH than number 7. So I'm going to place this as number 2 and this is number 7. Remember what I said, the greater the shift, the more electronegative the environment around that carbon. Right, now let's look at carbon number 3. Now that's a good one there. Now that one there, right, let's deal with that one first. That is a carbon that has a carbon above it in the double bond and a carbon next to it, which is attached to COH. Now that's not really attached in a very electronegative environment. So that will have the lowest chemical shift. And that is indicative in the data table where CC bonds have a range between, I'm looking at the table now, so around about between 10 up to 60, up to 70. So that one there, number 3, fits perfectly. So that means we're left to assign number 5, number 6, and number 4. But how do I know which is the most electronegative? Even though we're not required to group these, but we're going to give it a go. So this is going to be the most electronegative carbon, or the one that's in the most electronegative environment of the 3, and that one there will be the least. So if we look at number 6, so number 6 is directly on the OH, and the next door neighbor is the CC double bond. So that one there is probably going to be the one that is in the middle. Carbon number 5 is attached to a COH, which is right next to a carbon and another COH, and then next to carbon number 4, which is on a COH. It's between 2 electronegative environments and is directly attached to the OH. So that one there is probably going to be number 5, which means the last one, number 4, which is COH, which is just next to carbon number 3, which is just a CH2, which is not particularly electronegative, would be number 4. But we could argue positions 5 and 6 because number 6 is next to that double bond, which is mildly electron withdrawing. But then number 5 is on the COH, which is between another 2 COH groups, number 6 and number 4. So those 2 there, they would be the difficult ones to distinguish. So there we have it. We have the most electronegative is the carboxylic acid carbon, and the least electronegative is number 3, which is just a CH attached in that acyclic alkane with a double bond. This is one of many spectroscopy questions that I've gone through, you need to go on to know the other carbon NMR example I've done, plus the proton ones. So those links are below. Off you go, and I'll see you in the next one.